Good afternoon, everyone. I welcome all viewers to the 19th Vyakhyaan in the Pyaril Ka Amrit Vyakhyaan series of the online lectures or Vyakhyans. This series of 75 lectures began on 4th of August this year and is being organized every Wednesday at 4 p.m. To celebrate the Platinum Jubilee of Foundation of PRL. The Vyakhyans are delivered by eminent speakers from India and abroad from diverse fields of science, engineering, arts, and literature. Today, we are honored to have a very distinguished speaker for the Amrit Vyakhyaan, Padma Shri Professor Rohini Godbole, who is an eminent particle physicist and currently working at Center for High Energy Physics, Indian Institute of Science, Bengaluru. On behalf of the Director PRL, my colleagues, and also on behalf of the Amrit Vyakhyaan Committee of PRL, I extend a very warm welcome to Professor Rohini Godbole. Thanks, Professor Godbole, for gracing our celebrations of PRL at 75. I would now like to invite my colleague, Professor Shubhavati Goswami, to introduce the speaker to the audience and to request her to deliver the 19th Vyakhyaan in the Amrit Vyakhyaan Mala. Thank you. Professor Goswami, please.
Thank you very much, Professor Srivastava. It's really my privilege, honor, and a pleasure for me to introduce Professor Rohini Godbole. Professor Rohini Godbole is currently an honorary professor at the Indian Institute of Science, Bangalore. She is a theoretical particle physicist who has spent time at various universities in India, Europe, and the US, including CERN, Geneva. She has worked extensively over the past 4 decades on exploring the standard model of particle physics and the physics beyond it at the colliders, authoring more than 300 publications in refereed journals and archived preprints, including a graduate-level textbook on supersymmetry. Her pioneering work on probing hadronic interactions of photons at colliders provided important insights for the designs of the electron-positron colliders. Her suggestions to probe the standard model and the beyond standard model physics at colliders have been used in various experiments at different colliders. She is an elected fellow of all the 3 science academies of India as well as the World Academy of Science. She has been the council members of all the 3 as well as the vice president of the National Academy of Sciences, India. She has been the chief editor of Pramana, Journal of Physics, brought out by the Indian Academy of Sciences, and members of various editorial boards of national and international journals, and also of a number of international scientific advisory bodies, such as the High Energy Physics Advisory Panel in the US, the International Detector Advisory Group for the International Linear Collider, or the Advisory Board Oxford Research Encyclopedia for Physics. She is the recipient of the 4th highest civilian honor of the Government of India, the Padma Shri, first woman to receive it for work in physics. Recently, the honor Ordre National du Mérite was conferred upon her by the French government. Degrees of D.Litt have been conferred upon her by old universities like the SNDT Women's University, Tilak Maharashtra Vidyapit, and DSc is to be conferred by the IIT Kanpur soon. She is also an avid supporter of women in science and worked in a number of ways to facilitate more numerous and effective participation of women in science. This includes bringing out a book, Leelavati's Daughters, containing autobiographical sketches of Indian women scientists, as well as leading surveys to determine why women drop out of science after doing a PhD. These have provided some interesting insights on the issue of women in science. She also chaired the committee which drafted discussions on equity and inclusion in India's science, technology, and innovation policy of 2020. Personally, I have known Rohini for a long time, since I was a PhD student, and she was really an inspiring example in front of all of us, especially women. And she has really inspired us in many ways, and I still remember the way she cajoled me to submit the contribution for Leelavati's Daughter, because I was not finding time, and Rohini told me, Shubhavati, you cannot be more busy than me. So after that, I really submitted the article, and I am so happy now that, I am part of a history. So I really feel this was offline, and Rohini was here with us all, but we have to do the best under the circumstances. And with this, I invite Rohini, Professor Rohini Godbole, to give this Vyakhyaan.
Thank you very much, Director PRL, as well as the Vyakhyaan committee, and Shruba for giving me such a generous introduction, and my many, many friends whom I see on the screen, as well as in the list of participants. I won't go taking names because that would cut into the time. That kind of tells you how many friends I have at PRL. And therefore, actually, I think I am also missing an opportunity to come to Ahmedabad, which I would normally do every now and then. But well, we have to do the best we can. So I'm really glad to be giving this talk today. So now comes the exciting part. I'll try to share my screen. So bear with me. This always causes me excitement. Very good. All right. So the idea is that I would speak, as I have given the title, Shedding Light on Dark Matter in the Universe. But as you will see, in fact, that the subject is so vast that I have decided in the bracket that I will concentrate only on the small part that I do understand to some extent, and that is how can one shed light on the dark matter at the Large Hadron Collider. But of course, you need to know the bigger picture to look into and sort of take a close-up in a small part of a big photograph. So what I will do is the first part of the talk, I would kind of try to set the bigger overview first as to what are the current frontiers of exploration, theoretical and experimental in high energy physics. Then I will try to argue to you why dark matter is perhaps at the forefront of these frontiers. And then I would try to tell what are the kind of questions that it asks of the theories. And then, of course, since we don't understand it, that I will also say that this is one thing which particle physicists and astrophysicists really do not understand. So therefore, what kind of questions the existence of this dark matter poses us? And to answer those questions and sort of see whether what part of our understanding is correct, you have to do experiments. And that is the hunting for the dark matter, as it were. And then what can the Large Hadron Collider do in particular? So the elementary particle physics today, at the end of, beginning from the discovery of the electron, which was now more than 100 and, I don't know, 130, maybe 35, 50 years ago. Today, we have arrived at an accepted worldview of the fundamental particles and the interactions among them. We know that the fundamental particles in the universe are the quarks and the leptons. That is what everything is made up of. And they talk to each other, or they interact with each other by exchanges of force carriers. And these force carriers happen to be spin 1 particles too. This itself is a big discovery of the 20th century. And those force carriers are the photon, the W and the Z boson, and the gluons, and not last but not the least, the omnipresent Higgs boson, whose discovery in 2012, already 10 years ago, kind of completed this worldview. Now, you would say, all right, 100 years it took for the world of particle physicists to know what is the, as it said, periodic table of particle physics. So what? Why are you jumping up and down about it? The reason one jumps up and down about it is that this fact is not just of importance and interest to particle physicists alone, but the laws of particle physics, which have been discovered over the past 125, 30 years, and which have been found to be, functioning at distance scales of Fermis, which is a nucleus or distance scale smaller than a nuclear size. These laws, they seem to be of relevance to understand things that happened on cosmological time scale, that is things that happened at the beginning of the universe, or things that happen at astronomical distance scales, like today at millions of megaparsecs and above. And just to give you a feeling, 1 parsec is about 300.27 light years. And if you remember that sun is only 8 light minutes away, that means it takes the light from the sun to reach us only 8 minutes. Then you can now scale yourself from Earth to sun distance, which is 8 light minutes, to 1 parsec and megaparsec. So this is really huge distance scales, and things that happen in the laws that function at the core of an atom, at the core of a nucleus, seem to be of relevance to decide what is the energy that is released from sun. How is the functioning of the energy release from the sun? So this is what happened, as I said, at the beginning of the nucleus, at the universe. So in fact, the same laws actually, along with astrophysics, along with cosmology, help us to answer questions such as how did nucleons form? How can we explain the relative abundance of different elements in the universe? And by universe, I mean, of course, stars, galaxies, us. And the answers to these questions are actually available now in terms of astrophysics, in terms of cosmology. But along with those two things, we need the known physics of the standard model of particle physics. So this small little box that I have written here is actually required. Knowledge of that box is required for us now to begin to start answer questions about what happened at the beginning of the universe, or what's happening right now at the heart of the sun, or further. And in spite of this fantastic and amazing success of particle physics finds itself today in an extremely peculiar place. And I first wrote this slide 10 years ago, and I think the situation is now even more true than it was 10 years ago. And that has to do with the fact that many, many more results have come from the Large Hadron Collider. Now, I can describe this by stealing a line from Tale of Two Cities. I hope some people have read the book. This is a book written by Charles Dickens. And the book begins by saying, it is the best of the times, it's the worst of the times. So it says it was, because it was talking of time that around the French Revolution. But we can just say it the same way. It is the best of the times for particle physics, and it's actually the worst of the times. Now, why is it the best? Of course, we have found the standard model Higgs. We have proved the standard model of particle physics. And why is it the worst of the times? Because we have had not even a glimmer of particles or interaction beyond the standard model that was promised by the observed properties of the Higgs. Things have changed a little bit now. In the last 2 years, we have got some whip of things that don't agree with standard model quite, but they are not in line with what we had thought, we had expected based on some theoretical arguments. So that is the situation of particle physics right now. But the achievement of the last 100 years is that the entire, I should go back to this, my little box, the entire mathematics of how to describe the interactions among these fundamental particles actually can be written now in an equation which fits on the back of a t-shirt which you can buy in a curio shop at CERN. What is this? All of us have learned physics at some point or the other. We know, for example, that equations of motion of particles under action of a force in the case of mechanical systems can actually be written in terms of a Lagrangian. Now, this is the Lagrangian of all these fundamental particles and all the force carriers. Since all are fundamental, you can write this Lagrangian, and the equations of motions or the equations of force can be just derived from this little equation. So this is, as I said, the state of particle physics. So it should be again logical to ask, does it mean that the journey that started with the discovery of the electron is now over? and we can all say, okay, particle physics no longer exists as a discipline, does not need to exist. It can be closed shop and nicely tied in a bow and given to humanity as a nice little present. Actually, the answer is no. And why is it no? It's not only because particle physicists like to keep themselves occupied or busy or keep themselves having jobs. There is more reason than that. And that reason is that when I told you that the same laws of physics that we find here or that are enshrined in this Lagrangian are capable of, in principle, providing an understanding of the structure formation in the universe, of the baryon nuclear formation of nucleons in the universe. When I told you this, I can also tell you that while there is a very nice qualitative understanding of a lot of these phenomena, there are actually many cosmological observations which lack an understanding or a quantitative understanding. Either sometimes understanding is completely lacking, and that's the story with the dark matter, or we have an incomplete understanding in the framework of the standard model, and that's like the baryon asymmetry in the universe. And these puzzles, why are they relevant to particle physics? These are cosmologist puzzles. These are astronomical puzzles. They are of relevance to particle physics because of the cosmic implications of the theories of particle physics. Because theories of particle physics actually have relevance to what happens in cosmic scenarios. And Bethe, Gamow, and Weinberg are actually the three giants who pioneered these cosmic connections of nuclear and particle physics. And now that has become the order of the day for many of the particle physicists. So these are extremely pragmatic reasons why we think that there is physics that is beyond the standard model. That means there are particles and interactions that go beyond the standard model. That means there is physics, there are particles, and there are interactions beyond what is written in this box. So there is physics beyond standard model. We have no doubt about it. Now, the challenge to particle physicists is whether they can try to see what that physics beyond standard model is and how that physics, you infer that physics from the cosmological observations which still lack an understanding. That's the question. So what are the cosmic reasons to believe in this physics beyond standard model? One, and the foremost one, is actually dark matter in the universe. What is meant by dark matter? I will actually go in great detail, but in one line, there seems to exist an uncontroversial evidence that there exists matter in the universe that does not shine. That means it has no electromagnetic interaction. And this is what is called as the dark matter. This actually got Nobel Prize in 2019. There is a lot of work in PRL on the subject, in fact. The other one is matter-antimatter asymmetry in the universe. Even though at the beginning of the universe, there was an equal amount of matter and antimatter, because in the beginning, there was only radiation, and radiation treats matter and antimatter completely equally. Therefore, in the beginning of the universe, there was equal amount of matter and antimatter. But in today's universe, we know that we have only matter. I mean, if we had started having antimatter in our own universe, we would have started seeing Diwali fires everywhere. So obviously there is no antimatter in the universe, and there have been measurements. So matter dominates over antimatter in the entire universe. The last but not the least, universe seems to be accelerating. And in my talk, I would actually focus only on these first. But these are the three very important questions, puzzles that I referred to that are there. These are the three cosmic puzzles. Now, from the perspective of a particle physicist, apart from these cosmic puzzles, there are actually other reasons to expect physics, namely interactions and particles, beyond the standard model. I'm not going to discuss them in detail, but as a particle physicist, my heart won't let me go forward unless I tell you what those reasons for a particle physicist, which are very important. One is what particle physicists always call, and I would say that sort of very simply without giving the details, is why the Higgs boson has a mass which is comparable to the mass of the W and the Z and not much higher than that. That's a question that particle physicists actually, it's a deep theoretical question. Then the fact that the neutrinos have been found to have non-zero mass, and one needs to get a clear understanding about the masses of the fermions, because the neutrino masses and the top quark mass, the ratio is 15 orders of magnitude, and particle physicists would like to understand why such huge ratios exist in the masses of these fundamental particles. Then do all the three couplings meet sometime at some high energy? Do they ever become one and the same? And last but not the least is inclusion of gravity in the picture. And what is very interesting is quite often solutions to these cosmic puzzles and the theoretical ideas which have been introduced to address these theoretical problems of particle physicists actually are intertwined. And that is why these questions can be understood or can be addressed in a particle physics laboratory. So let's begin now with dark matter. And the contents of our periodic table, as we know today, and which I sort of very enthusiastically told you a lot about, they account only for about 5% of the total matter in the universe. And the astrophysical evidence is very, very convincing. And in the standard model, there is only one particle which could be neutral and which could have been dark matter. But experimental information, which I will actually go and discuss, indicates that dark matter cannot be neutrinos. And therefore, we need at least one particle beyond the standard model. That is, the existence of the dark matter tells us that we need at least one particle beyond the standard model. And we can draw this conclusion only because we have understood the interactions that all the standard model particles have completely. So this is the energy budget of the universe, and I'm sure all of you have seen this picture time and again, but I would like to show it that right now we see, this is from measurements from Planck experiments and many such things, where we see that the total observable matter, of which, quarks and nuclear, the matter that is made by quarks, electrons that I talked about, is only 5% of the total matter in the universe. 26.8% of the total matter in the universe is dark matter, and the remaining actually is what is called dark energy. But I will not even touch upon that. I will only talk about this 26.8% of the total matter in the universe, which is dark. So where did the idea start from? The astrophysical evidence first came from Lord Kelvin. And I will not repeat kind of what Lord Kelvin had said, but he had sort of inferred and postulated that there might exist some matter which we cannot see optically. But for most of us, the idea of dark matter started from Zwicky, who actually called it first time Dunkel material. And what was his reason? Because he tried to measure the mass of the galaxy from the galaxy dynamics. And then he saw that there must be much more visible mass if the galaxy had to be held together by gravitation at the velocity at which the different galaxies in a galaxy cluster, for example, were rotating. Okay. So because we know that by Virial theorem, gravitational and potential energy and kinetic energy should be equally shared by a system. And therefore, the fact from the major velocity, he saw that unless there was a potential energy in the system to hold everything together, these galaxies should have just flown apart. And therefore, he drew the conclusion that there is more matter than what we can see. But this whole idea of dark matter was finally, there are a few other investigations, but I won't give you a full history. It was put firmly in place by measurements by Vera Rubin, who passed away a few years ago. And what did she measure? She measured what are called rotational curves of galaxies. So she did this in spiral galaxies, which are the most common galaxies, in fact, that are known. So the stars in a spiral galaxy rotate. They rotate about the center. Now, you normally expect that the stars which are closer to the center here, let's say the star N, which will actually rotate faster than the star F, which is far away. Why is that? Because you can just use ordinary Newton's law and you can convince yourself that the velocity of rotation of a star in about the center of the galaxy will be given by gm by r, where g is the Newton's gravitational constant and m is the mass inside. So if f is at a distance rf and n is at a distance rn, then one expected that if rf was 4 times rn, then f should rotate twice as slower. But in reality, it becomes quite different. That just meant that the mass that was enclosed when the star was rotating around the center was increasing as the radius r of the orbit is increasing. And in fact, if there was no dark matter, the velocity of rotation should have gone down with distance, whereas in practice, the velocity of rotation was seen to remain constant as the distance increased. And this was a measurement by, this is Vera Rubin at work in her lab. This is the measurement in 1970, which was a measurement in galaxy called M31. And this was the spiral galaxy, as I told you. And these are the other people who had made measurements, Babcock and company, etc. But this measurement is made by Rubin and Ford, and what they see, and then later on by Carrigan et al. And one begins to see that the velocity does not really drop down, but velocity remains constant as you go further and further out. Now, this is radius in arc minutes. We won't understand these units, but now I will show you a second plot in the galaxy M33. This is much later, and now this is the distance in light years. So 10,000, 20,000, 30,000, and 40,000. And expected from just the visible disk, the velocity of rotation, this is the rotation curve, should have gone down like this, whereas the observations made from many different sources. Now, these her measurements were from starlight, but these are measurements from other sources. And now you see that the velocity does not decrease. In fact, it slightly is increasing here or flattens out. So this particular behavior of the rotation curve is indeed what actually is the first strong evidence for the existence of dark matter. What it means here is that if the mass that was enclosed inside this was visible mass, which you can figure out, which astronomers can figure out, then the velocity should have gone down. And since the velocity is not going down, you know that there must be mass that we cannot see, and that's the dark matter. In fact, there are many other evidences for the dark matter. I'm just showing 2 pictures here, but I will describe these 2 pictures in my next 2 slides. And this picture here is collision in bullet cluster. And here, this is actually the Planck cosmic microwave background measurement of the anisotropy. And I will discuss this in the next slide. But all I want to say is that this gives you the evidence of dark matter at the distance scale of megaparsec, going from the kiloparsec here, and the Planck CMB anisotropy gives you the existence of the dark matter at the scale of the universe, which is gigaparsec. So what is this bullet cluster? In this bullet cluster, there is a galaxy collisions that has been pictured, and this is the photograph has been taken in 2 ways. One is a gravitational lensing. The red is the image in X-rays, and the blue is the picture that has been taken by gravitational lensing. So blue is the picture that is sort of reacts to only gravitation, that means only mass, whereas red is the picture which reacts or reflects only the visible matter. And here you see that there is much more extent to which the blue picture extends than the red picture. So that tells you that there is dark matter. So what is gravitational lensing? Now actually this method of gravitational lensing is being used more and more. More and more distant galaxy clusters are being seen, and people are trying to obtain information on the dark matter in the universe from the effect of the intervening bodies on the image of this cluster. So this dark matter imaging is like we see crystal structure through diffraction patterns. You know, this is a bit bending of light, bending of gravitational, bending of light around this is what is being seen. And the last but not the least is the measurement of cosmic microwave background radiation and isotropin. And that, as I said, it's a very long story, so I do not want to go into it, except by telling you that this has a connection with the formation of structure of galaxies, stars, and so on in the universe, in the early universe. So in some sense, the cosmic background radiation takes a picture of the universe all that time back, and hence all that distance away. And one has seen evidence of dark matter in that also, as a result of which there is a dark matter has been seen at the kiloparsec distances. Dark matter has been seen at the cluster of galaxies, which is megaparsec. That's the bullet cluster I showed you. And the observable universe, which is at the gigaparsec. We actually do have dark matter even on the sun or the earth, but the density is so much more higher in places like galaxy clusters and centers where you want to really try to look for it. So what do we know about dark matter? Frankly, we know very little. All we know from all this series of experiments, and beautiful experiments, very difficult experiments, is that dark matter actually exists. Now, there is no question that dark matter exists, that it forms about 26.8% of the total energy budget of the universe. That's also pretty incontroversial. Then the dark matter velocities are about 200 kilometers per second. So that is also now measured. But what is definitely true is that direct experimental evidence is all based and all indicates and all proof only for their gravitational interaction. Okay. And it is electromagnetically neutral, and it has got to be stable on the scale of the lifetime of the universe. That means about a few billion years. And last but not the least, it has got implications for structure formation in the early universe. Now, what do I mean by that? Again, on the next slide, I will try to explain it to you. But basically, this is all that we know. We don't know what its mass is. We don't know what its interactions are other than gravitational interaction. And that is the thing that we are now trying to understand. So this sort of pictures, I've taken this picture from particle data group, PDG. And this is where the universe began in a big bang. This is the inflation period, and it started expanding. And this basically, the point is that the dark matter has had implications. For example, how the structure was formed here, how the dark matter came into being in the universe depends on this early cosmology. And I will again give you a few examples, a few qualitative arguments how it happens. And therefore, when you look at the dark matter dynamics or the trying to get information of the dark matter, you would actually want to look at what happens in these early periods of the universe, and you would want to understand what happens during the structure formation. So in the early life, the universe, it's all radiation. In this expanding and cooling universe, slowly baryons are formed here, okay? This is where baryons are formed. And then finally, the galaxies and clusters are formed. So initially, the rate of annihilation and creation is in equilibrium with each other. So as many particle pairs are being created, as many are being annihilated. Then the abundance of a particular particle type remains constant and is determined by the temperature of the radiation. But a universe, as I said, is also expanding. It is also cooling. Now, because it's expanding beyond a certain time, the created particles cannot find the partners to annihilate. And in which case, that particular particle species falls out of thermal equilibrium with the radiation. And after that, the abundance of the species will not change because it has got disconnected from the radiation. And the temperature at which this will happen is actually determined by the strength of the interaction, by the spin of the particles, and so on and so forth. So this is determined by particle physics. This is what I meant by saying that in this early time, when the universe is expanding and cooling, laws of particle physics are actually playing an important role. So then these relics get left over from the early universe. When they fall out of equilibrium, the number stays constant, and therefore the universe is just expanding, and this particle species abundance then does not change. Now, since dark matter had to be created in the early universe, because initially there was only radiation, it must have had some interactions other than gravitation, but we really don't quite know what those interactions can be, and that is the game that we are trying to play and understand. The reason dark matter particles have, or dark matter has implications for structure formation is that the dark matter actually provides gravitational potential wells where the matter can get together and structures like stars and galaxies can be formed. And that is why the cosmic microwave background radiation anisotropy can give us some information about the total amount of dark matter that has to be present in the universe. So what I want to tell you in this very qualitative discussion is that the expected relic density, that is, the relics, the density of the relics, dark matter density, the expected relic density predictions, which you could calculate theoretically, will be determined by the theoretical understanding of the early universe, as well as the particle content of the particles in the of the early universe and the interactions among those different particles. So this is truly an astroparticle beast. It needs to know knowledge of astrophysics, cosmology, and particle physics. And there is a lot that we don't understand. It's a very active area of research. And actually, Shubhendra and his group at PRL have worked very actively, particularly with the cosmic connection ideas. So strictly speaking, we have only evidence for the gravitational interactions of dark matter, but we have no information about its mass. And we only know what is the total matter that is there in the dark matter form, but we do not know what is the density, number density of these dark matter particles. What is really liked is a number which would fall out of thermal equilibrium with radiation in the early universe when the particle itself is non-relativistic. So if that has to happen, then that particle needs to be heavy, because when it falls out of thermal equilibrium, it should be non-relativistic. And that is why neutrino, which would have been a very nice dark matter candidate, we know it has very small mass and it just cannot be the dark matter, the neutrino that we know and love, the standard model neutrino. And this heavier dark matter candidate is called cold dark matter, CDM. And this weakly interacting massive particle paradigm called the WIMP is actually ruled for a very, very long time. From the beginning, it came out and particle physicists absolutely loved it. So let me try to tell you why particle physicists loved it. And this is where my own interaction with dark matter really begins. So this is the current number that I'm giving you, that the Planck measurements and the anisotropies of the cosmic microwave background radiation actually tell us that a scaled number for the mass density and the relic density is 0.120 plus minus 001. Let us not go into the details of what this number is. But if I name the candidate dark matter particle as chi, in a theoretical model, without knowing the details of the model, you, by the very fact that such a particle exists and that it gets created and annihilated, etc., as I told you, and it falls out of thermal equilibrium, using these ideas, you can actually calculate this same number that the experimentalists are measuring, and that number looks like this. It's various constants that are involved, and this is 3 into 10 to the minus 27 centimeters square per second divided by averaged velocity averaged value of the annihilation cross section of the dark matter times the velocity itself. And the couplings of the dark matter particle which will decide the annihilation cross section, and therefore this product will actually decide the relic density. Okay, and this relic density, therefore, through this formula, calculated or predicted relic density will depend on the model through this object, and different combinations of G chi and M chi can produce the right relic because they will give rise to the same sigma annihilation at a given velocity. And the sigma annihilation is what is controlled by the particle physics model. So now you begin, and many of the constants here are actually governed by cosmology. So that's why this quantity, the relic density itself, is an astroparticle physics quantity. Okay, and therefore some parts of this expression depend on the assumptions about cosmology, and this part depends on the particle physics model. So this is so far what we know. Now there is a solution in particle physics which was actually suggested quite a few decades ago to keep the Higgs boson light. I'm slightly moving my these things now to a male motivated model of cold dark matter, and I will come back to this formula in a minute, why am I doing this. So here the idea is called, this is idea called supersymmetry, that associated with every particle, there is a supersymmetric partner. And looking for this dark matter candidate at the Large Hadron Collider can be a window for supersymmetry at the Large Hadron Collider. Because this guy, the lightest supersymmetric particle, is actually a tailor-made candidate for dark matter. And why is that? That is so because in supersymmetric extension of standard model, naturally there exists a particle. The particle is neutral, the particle is stable, and in fact, it has annihilation cross-section times velocity of the order of 10 to the minus 26 centimeters square. And then you go back and say, aha, if this is 10 to the minus 26 centimeters square, then indeed I am, and the velocity, I told you what the velocity is in the early universe, you have to take an average, and you will realize that you say, my God, then therefore this can be a very tailor-made candidate for cold dark matter. So in fact, the theory, as I said, theory really had the ready-made cold dark matter candidate, and that's what sort of, set the pulse of all the particle physicists racing when this formula was first derived. And now what has happened since the discovery of the Higgs, LHC has indeed looked for other particles that supersymmetric theories predict. It does not only have the dark matter candidate, it has a plethora of new particles that are to be that should exist, and their masses were supposed to be, around 1000 GeV, which is 1000 times the mass of the proton. And looking for them at the LHC was considered as one way to look for the physics beyond standard model and looking for supersymmetry. We haven't found it so far by looking for the partners of top quarks, which would lie with masses around 1000 GeV. But we haven't yet finished quite looking for the dark matter particle that this supersymmetry might actually predict. And that is the part or forms the subject of my remaining talk. So as I said, the theory does not, what is interesting is that the theory does not tell us what will be the masses of this dark matter particle of the CDM, but we know that the natural expected values for these masses are between, let's say, 10 to 1000 GeV. And those are the dark matter particles, and their their cousins and sisters in supersymmetric models are the things that we would like to look for at the LHC now, because all the remaining ones, which are not cousins and brothers and sisters of the dark matter particle, I can go into question and answer more separately what I mean by that. We will then say that look for these new particles. So this is the idea. Now, this is what supersymmetric dark matter is. But I should also tell you that however well motivated, it is just one model. And from astrophysical and cosmological arguments and all the other measurements, we do not have any confirmed indication of its mass in the measurements. And there is a range of masses that are allowed. And for different ranges of masses of the dark matter, there are different models. Supersymmetry happens to be a nice model where the mass of the dark matter particle is between 10 and 1000 GeV. But the important thing is that they all have to give us a Rayleigh abundance in agreement with the measurements by Planck. So now there are two parameters. One is the dark matter mass and other is the annihilation cross-section. And the annihilation cross-section, as I already told you, depends on the particle physics and the other particles present in the model. So that is where we are as far as the predictions of Rayleigh density go. Now, I've taken this slide from my friend Hitoshi Murayama, who says, and which is true, and I agree with him, that if you were completely agnostic about supersymmetry or anything at what the dark matter model is, then the allowed values for the dark matter can vary over 36 orders of magnitude. But the WIMP, as I told you, that I talked about in a big way, is this small range, where supersymmetry kind of predicts the dark matter candidate and has a very ready-made dark matter candidate. But there are this whole lot of other theoretical ideas which predict dark matter candidates over this entire mass range, and we really and truly do not know what is what. Okay, that's where things are. And in fact, As I told you, the important thing is the annihilation cross-section and the mass, and the theories have predictions for dark matter particle over entire mass ranges like this, and the theory predictions also go all over the place when you start predicting the dark matter cross-sections. But here I should say that there are 63 orders of magnitude in cross-section and 51 orders of magnitude in mass. If I were trying to be completely agnostic and go let everything be allowed, everything that is not forbidden, let that be allowed, then we would have this kind of situation. But I should also tell you, without going into the details, not all the models will give signatures at the LHC, and not all the models are well motivated. All right. So how would we want to decide what is the correct story, if any, among this multitude of models of which I don't even want you to look at the names? How are we going to decide? Is it SUSY, which I love and cherish, or is it something else? Is it axionic dark matter or whatever? And there are some actually who argue that simply modifying theory of gravity may be enough to explain dark matter. And these are modified versions of what is called MOND. But I'm going to go with the hypothesis that dark matter actually requires existence of additional particles. So how do you detect this dark matter? So through gravitational effects, you have kind of inferred its existence. But if you want to do an experiment and detect it, how do you detect it? You can detect it directly. That means a dark matter particle interacts with a standard model particle. That is, the dark matter particles are impinging, make a detector on the Earth. They hit the detector, and then you have a scattering of this dark matter particle from the detector. You detect this scattered standard model particle, because that you can detect. And this would then give you the direct detection. So this is called shake it. That is, you hit the standard model particle or your detector with a dark matter candidate. Then the second one is, you at a collider, you collide standard model particles and produce a pair of dark matter candidates and something more. And then you try to study the production of these dark matters at the collider. How that happens, I'm going to come in a few seconds. And indirect detection really means that you take annihilation of two dark matter particles which produce the standard model particles, and what you detect are the standard model particles. So the dark matter candidates annihilate, produce the standard model particles, and the detectors detect the standard model particles. This is called indirect detection, because what you detect are only the standard model particles, and you try to see whether it is consistent with a hypothesis that it was created in a dark matter interaction. Collider production is standard model particles, and you try to see whether they are produced in your collider experiment. And direct detection is really getting a direct particle, hit it on a detector, look at the interaction with the detector, and try to see, measure, or find its existence. So there are actually huge experiments that are being planned. The direct detection experiments are actually, these are two pictures that I'm showing you. One is a xenon experiment, and this is the inside. Then there are collider searches, okay? These are the LHC, which I will talk in detail about. There is one thing that I will not discuss, not because it's not interesting enough, but lack of time, and that is, and also lack of expertise, I guess. Indirect detection of dark matter particles producing in their collision and annihilation, producing standard model particles. There are also these high energy neutrino experiments, ice cube like experiments, which will also look for indirect detection. So this is indeed the story. Now let me go. I am going to discuss only the direct detection and collider searches. So how can we detect this dark matter particle on the Earth? As I said, this particular hypothesis or this particular suggestion works for dark matter particle masses in the range of 10 to 1,000 times, which are 10 to 1,000 times heavier than the proton, that is 10 to 1,000 times GeV. What you do is that you use a heavy nucleus, then the WIMP is incident on this heavy nucleus, and the heavy nucleus will recoil. And you measure the recoil velocity of the nucleus, and then the expected typical recoil energy for a mass of the WIMP between 10 to 1,000 times 1,000 GeV, the recoil energies of the WIMP are about, of the nucleus are about 100 keV. It's a difficult experiment, but that is actually the experiment that people are doing. And modification of detection techniques might increase the possibility of the moving to the smaller range, smaller than 10 GeV, and that is the current kind of frontier in the experimental front. But this experiment is actually, these are giant experiments, and they have been now, they are right now at the forefront of the dark matter detection. And this has actually, what I show you, they have not seen dark matter, and as a result of that, they have only given limits on the WIMP nucleon cross section as a function of the mass of the WIMP. And now, this is the limit that it has given, and this is from 2019, and now there are big exclusions, and this is a situation that has developed extremely rapidly in the last 20 years, and we expect still progress in this. And now you go and you think of your favorite model, construct your favorite model, and see what it would have predicted for this experiment, and is it consistent with this exclusion. That is the moral of the story. Now, before I tell you this, I should also tell you, for example, what are the predictions of the, say, supersymmetric extension of the standard model. This figure is very, very busy, but forget about all these islands because I don't want to go into those islands. But otherwise, it is the same thing, sigma WIMP nucleon cross section in centimeter square. This is also the WIMP nucleon cross section. And these are the different, you can see the familiar face shape of the exclusions. And for example, for supersymmetric standard model, we expect signal rates in this green region. So that is the point. Now you do this experiment, and when you do this experiment, you would be probing existence of a dark matter. Say, for example, at this point, what it says is that a dark matter candidate of 100 GeV with a cross section bigger than 10 to the minus 46 centimeters square has been ruled out. Now you go to your model and try to see what region of the parameter space does this observation correspond to. So, now I move to hopes from LHC, and I must say here that in 1986, when the LHC was originally designed, one had designed the LHC, of course, to find the Higgs, but one had also hoped that one will find solutions to the dark matter problem, to the variant, our particles that we were predicting for the explaining the dark matter, for explaining the baryon asymmetry in the universe. These models are really, really old now, and therefore we were thinking that LHC was going to be one answer to many, many questions. And now LHC has come and gone. 10 years ago, we have climbed this mountain. We have reached on the Higgs. But what we find is that from a distance apart, all these mountains looked close enough. Now we find that the mountain of the dark matter and the baryon asymmetry in the universe is still further apart, and we have to still do more experimentation. So now I want to come in the last 10 minutes on concentrating on a very small part of the story as to how one can probe the dark matter candidate in supersymmetry through joint experiments at LHC, the direct detection experiments, and the upcoming future colliders. So now I know that I'm going to be in a little more, particle physics specific discussions, and I will discuss them in the context of model of supersymmetry, because that's what I have been, as I said, I know a little bit about. And the advantage of discussing this in the framework of a model is that in the same model, controlled by the same parameters, the relief density calculation, direct detection cross sections, even indirect detection cross sections, and the LHC signals are all controlled by the same parameters. So one can study a given parameter point in the parameter space of the model and ask for its application for relief density, for direct detection, for LHC searches, and for indirect detection. And then you ask whether that particular point in the parameter space is still allowed by the non-observation and by the observed relief density. That is the question that we would like to ask. Of course, the results of what experiment you do for direct and indirect detection doesn't depend on your model for the dark matter, except it depends, how you interpret it depends on the model. Whether your dark matter particle is a scalar, whether your dark matter particle is a spin-off object. These are the kinds of things or whether spin 1. That's very unlikely story, but still. So these are the interpretations will depend on the model, but the experiments themselves are the same, are model independent. At the Large Hadron Collider, some signals depend on the model of your dark matter, and some measurements or some signals are independent of the dark matter model. So how can you look for the dark matter at the LHC? There is a very simple thing that I want to tell you. Large Hadron Collider till today it has produced about 7 million Higgs bosons. Now, of course, not all the 7 million Higgs bosons get detected, but this basically now tells you now how the Large Hadron Collider studies have moved from finding the Higgs to study rare decays of the Higgs boson, because even if you can detect only 1/10 of these, you are still measuring close to 1 million Higgses. That means that if 1 in 1 million times a Higgs decays into a very particular, a different final state, that's called a rare decay, you should be able to detect it, right? So the question that now we have asked, particle physicists have begun to ask, is that are there additional exotic decays of the Higgs that will exist in the beyond standard model models, such that all the, one of the model, the BSM model was SUSY, for example. Now in SUSY, do there exist exotic decays of the Higgs? That's the question that you would like to ask. So actually, as I said, in supersymmetric theories, some decays exist of the light Higgs, where the Higgs decays into dark matter particles, which cannot be seen in the detectors. So this is a very strange decay. And in fact, and why? Because the dark matter particles, being neutral, do not leave tracks in the detector. So in general, their production is indicated by an imbalance, apparent imbalance of the momentum. We all know momentum and energy are conserved. So if there is an apparent imbalance, that means that the detector has not seen something. Now you could also ask, how do I know that the detector has not seen something? Because the particle was invisible for the detector, or the detector simply had a crack. So that is where the beautiful LHC detectors come into play. They are what are called 4-pi detectors, and they cover the interaction area completely. So if a visible particle decays, they are sure to catch it. They know the efficiency with which they will catch it. So when you see a large imbalance in momentum, you can normally translate it into the missing particle, production of missing particle. In supersymmetry, for example, the cascade decays of gluinos or quarks, which these are the particles which would have been produced with very large cross sections, and then that would have given rise to events with missing ET, because in the decay chain at the end of it, it would have produced dark matter particle, and that's the lightest supersymmetric particles. Experiments did not find anything here, and therefore we forget about it. Okay. Now here, the current data tells us that the constraints are only on the particles which had cascade decays, but that is the strongly interacting particles. But you could have lighter new particles which do not have strong interactions, and they might have been missed. Plus the direct production of brothers and sisters of the dark matter particles that I told you. And these specific signatures, what specific signatures you should look for will now depend on the supersymmetric model, since I'm talking only of SUSY dark matter. Model independent star strategies would be production of dark matter particles in association with other standard model particles, such that you make a pair of the dark matter particles, Higgs decays into a dark matter particle along with a Z. So the detector shows only a single Z or a single W or jets and a lot of missing energy. And those kind of events, what are called mono events, are the third thing in terms of which you can look for dark matter at the LHC. In the current situation, because the first has been, the cascade decays have been looked for and we haven't found anything, the current situation, there are two possibilities to look for the light dark matter. One is the production of a single WZ or jets in association with a lot of missing energy. So you look for invisibly decaying Higgs, which will also give rise to similar final states. And then SUSY dark matter, which is the lightest supersymmetric particle, look for its slightly heavier brothers and sisters, which could have gone undetected so far. So that is the idea. Now, actually, I'm not going to discuss next because these were my personal connections. But what I wanted to show you is that beginning from 2003, we had been suggesting how to look for an invisible Higgs at the LHC. At this time, the Large Hadron Collider had not found a Higgs, but we made these suggestions. And then we updated that in the 2013 when the Higgs was really found. And then we made some additional suggestions to that. And now, we have not seen any SUSY particles that were strongly interacting SUSY particles at the LHC. And therefore, one wants to now understand, are there any supersymmetric particles? Is there at least the one lightest supersymmetric particle that is present, which so first one would like to look for decay of the Higgs into invisible particles, as well as one would like to look for, as I said, the brothers and sisters of this lightest supersymmetric particle. So we decided to look critically at this light SUSY dark matter and how this can be probed or perhaps ruled out. And again, we did, I just want to display that over the years, the last 4 or 5 years, we have been working on this subject. And I will now skip actually what I would have liked to show you, but that is not really the, I don't really have the time. So what happens that in each of the supersymmetric model, because for each point, there are also different versions of supersymmetric models. The invisible branching ratio, that the number of times the Higgs will decay into unseen particles, is actually also related to the relic density. The same parameters control the relic density, and those parameters control the invisible branching ratios. And therefore, the observed limits on the invisible branching ratio can rule out certain values of the parameters. And at the same time, for certain values of the parameter where the predicted invisible branching ratio is still below the excluded limit, you can then predict signatures for the production of the lightest supersymmetric particle and its heavier cousins at the Large Hadron Collider. And you can check out by looking at the Large Hadron Collider itself whether there is these particles exist or not. And as I said, a given point in the parameter space actually tells, once you choose a point in the parameter space, it also tells you, in fact, it tells you the relic density prediction also. So in fact, we did this sort of very correlated study. And I want to just summarize this in this one slide, our results, that in the minimal supersymmetric standard model, the case of a dark matter particle, which is lighter than m Higgs by 2, which is lighter than 62.5 GeV, is actually extremely severely constrained. Once you put all the LHC constraints, all the invisible decay constraints, and the direct detection constraints coming from the xenon 1-ton experiment, as you actually find very small regions around m chi equal to mz by 2 and mh by 2 are still allowed. But for many of the points in the SUSY parameter space which are still allowed, one actually might need an additional particle to explain completely the observed relic. But the story is quite different if you think that the cosmology is different than the standard cosmology, or there are extended versions of the MSSM, which is called a non-minimal supersymmetric standard model. So this is just to show you that we scanned some millions of points, and then you saw, these very, very small, these are the small region number of points, small regions, which were still allowed by the dark matter detection experiments. In the case of NMSSM, actually a large variety of points are still allowed. These are all allowed points, and which give you a relic density which is reasonably close to the observed relic density. And what is being shown here, in fact, is what is the invisible branching ratio. And now you see here that this is the xenon n-ton projected limit. This is what is called the coherent neutrino scattering limit. And there is a large number of allowed points in the NMSSM parameter space, which will not be, which will be not reached by the direct detection experiments, but whereas they would be reached by this measurement of the invisible branching ratio. And better still, they will be also reached by the searches of the supersymmetric particles such as the LSP and its cousins at the Large Hadron Collider. I am not going to take you through the details of this calculation. And also, if I have non-standard cosmology, then also I have a similar result, that there will be a large number of parameter points in the parameter space which will be invisible, or in where these xenon experiments will be insensitive. They cannot be reached by these direct detection experiments, but luckily enough, they can be probed by measurement of the invisible decay of the Higgs. That is what these different colors correspond to. Or better still, they can be also probed at the Large Hadron Collider. This is just showing you the blue means that the entire region can be probed at the Large Hadron Collider. So again, it means that the regions which are invisible to the xenon n experiment can actually, direct detection experiment can actually be probed at the Large Hadron Collider, and the Large Hadron Collider will do its job. So the final conclusion for SUSY, a lightest supersymmetric particle, lighter than mh by 2, is still possible, and the WIMP paradigm for a light LSB is allowed by all the current data, that is the LHC data, the direct detection data, and the indirect detection experiments. And it can be actually tested at the high luminosity, high energy LHC, or the E plus E minus colliders, or the direct detection experiments. Even the non-standard cosmological scenarios can be tested at the LHC. And this is just one example of the dark matter studies at the LHC. I know one of the many ideas that are going around is that maybe sterile neutrinos are the dark matter. And actually, one of these ideas, in fact, was advocated by Subhendra. And the idea, in fact, has implications for structure formation. Now, supersymmetric partners of sterile neutrino, they are called nu-twiddle R. They can also offer themselves as good dark matter candidates. And they lead to also to a light SUSY dark matter. And in the SUSY context, it leads to a lot of interesting signatures, which can be then looked for at the Large Hadron Collider. So there are many paths to be pursued. And as Sherlock Holmes says, the game is afoot. The experimental exploration for the dark matter and developing a theoretical understanding. I hope I have convinced you why it has the topmost priority in particle physics. It involves particle theory, astrophysics, cosmology, precision cosmological experiment, precision astronomical experiment, and precision experiments at the Large Hadron Collider. So the quest certainly continues. Thank you very much.
Yeah, thank you, Professor Godbole. Thank you very much for this wonderful Amrut Vyakhyaan. And so it is a very difficult topic, and then you have made it in a very simple language. And the interest one can see that it has raised a lot of curiosity among the audience. From the chat box, I can see there are a lot of questions. And so what I will do, I will just read the questions one by one. And first from this YouTube chat box, and then from the people in this this WebEx studio. Okay, so first question is by Harish Ghadavi. So his question is, why should be there antimatter at the beginning of the universe formation?
Okay, that answer is very simple. In the beginning, you have only radiation. Now, you know that, for example, when the density of radiation is very high, two photons can simply create an electron-positron pair. And then they will create them in equal numbers. And if they have enough energy, which these photons do have, they're just going to produce those particles, charged particles, in their collisions. And then it's clear that the particles of one charge and particles of other charge are going to be in equal numbers. There is no way you're going to produce one particles larger in number than the antiparticles. So this is just a simple fact that initially you have electrically neutral radiation, that is purest form of energy, and that radiation, which is photons, is going to collide with each other and is going to produce electrons and positrons and quarks and antiquarks and W plus and W minus and the whole lot.
I hope he is satisfied with the answer. So my request to
there is no other answer as far as I know.
Yeah. So anyway, I mean, if you have further queries, you can again post your comment in the chat box. Then I can read again. So so that way it can be interactive. Otherwise, there is limitations. The crosstalk is difficult, not possible through this platform. So okay, let's go move on to the next question. The second question is by Manish Singhani. So his question is, what is the probability of the decay of the Higgs into the dark matter particle, and what could be the time frame for this decay?
Now, that's a very good question. Okay. Now, the time frame of the decay is the lifetime of the Higgs, and the lifetime of the Higgs is indeed extremely small. I mean, I can work it out, and all of us can work it out, but it's a very small number. So the lifetime doesn't change depending on the final state. What changes is the branching ratios, and that is where the probability comes into picture. That when a Higgs is produced, the most of the times it would like to decay into a BB bar pair, a pair of a B and an anti-B quark. Then sometimes a little less, it would like to decay into tau and a tau plus and a tau minus, for example. Or it would decay into one Z boson and one virtual Z boson. So this happens at the relative rate at which a Higgs boson decays into different final states. It's called the branching ratio. That is the total decay width of the Higgs boson, or the decay probability, if you like. The Higgs once produced is going to decay. So the total sum probability is 1. It is going to decay. It's not going to live anywhere long. So the sum of all the probabilities is 1. And the relative probability of each of the final states is the branching ratio. So, for example, a Higgs decaying into 2 photons is 1,000 times 1,000th of the decay probability that the Z will decay into BB bar. Similarly, the Z decaying into dark matter particle, Higgs decaying into a pair of dark matter particle, the probability actually depends on the model. For example, in supersymmetric theories, for a given value of the supersymmetric model parameters, the value can be computed. And these values can change anywhere between minuscule values like 10 to the minus 4, 10 to the minus 5 to 10 to the minus 1, or even bigger than that. So a model, now what you do is that you go and say, has LHC seen an invisibly decaying Higgs? And LHC says that we have not seen an invisibly decaying Higgs, and the branching ratio, if such an invisible decay exists, is less than 10%. That is the answer that LHC has currently given us. So what do? I go and calculate in my model what is the predicted branching ratio, and then I say all the points in the parameter space where my model predicted branching ratio bigger than 0.1 is now ruled out. And that is what I meant by that plot that I showed you, that some of the points that are allowed by all the constraints now, they can be probed either through direct detection experiments, or they can be probed with the measurement of the invisible decays of the Higgs. And some points which will be not reachable for the direct detection experiments in the parameter space will actually be reached by the measurement of the invisible branching ratio, because the E plus E minus collider can measure these invisible branching ratios to much lower amount, that even if the branching ratio is 1 part in 1,000 invisible branching ratio, a E plus E minus collider can actually measure it. So that is why these future E plus E minus machines are extremely important. And that's a very good question, by the way. And I hope you got some answer to the question. But otherwise, I would say that if you are interested in knowing some more details, I would direct you to the review article that I published in Springer just last year.
Thank you. No, related to the later part of his question, the time frame, can we say it is sub femtoseconds or
Yeah. I mean, I don't even know what the width is. If anybody remembers it, it's less than a few keV or something like that. So that would mean, I don't know, 10 to the minus 50, it has to be 10 to the 19, minus 20 seconds.
GeV inverse is 10 to the minus 26 seconds.
That's why I said my number in my mind is 10 to the minus 20 seconds.
Yes,
so thanks for confirming it.
Yes,
But
people in high energy.
Make the number because I may be off by 1 order of magnitude this way, that way.
Yes.
My memory is 10 to the minus 20 seconds.
Yeah. Community use the natural units in the high energy, but the people from outside,
10 to the minus 20 seconds. Okay. So that's good enough.
Yeah. Thanks, Mahanti. Yeah. Okay, so the next question is by Sandeep Sharma. So his question is, can black holes contribute to dark matter?
That's
Because
actually
they also
sort of,
cannot be
it's a
invisible.
good question again. It's a good question again. But from whatever I have understood, because this is where things go a little bit outside my ken, as it were, outside my field of knowledge. But I don't believe that black holes can explain the entire dark matter that appears in the universe. And that is where these gravitational lensing measurements, etc., play a role. But I won't be able to answer this question in more detail. Apart from the fact that they cannot form the entire dark matter. This I know for sure. And I also know where it comes from. It comes from the gravitational lensing experiments. But that is where my understanding is limited of this particular aspect.
Okay. So next question is from Harivats. So his question is, are we sure that mass of the visible matter is not underestimated?
No, I think that was actually for a long time the question. And as I'm sure, I mean, the astrophysicists know this much better, that till this bullet cluster collision of galaxies story came, and really the cluster collision showed the distinct difference between X-ray image and the gravitational lensing image, people were actually wondering whether we are estimating the visible matter wrongly, because that is associated with saying that the gravitational interactions are slightly modified. Your estimate of visible matter, when will it go wrong? It will go wrong only if it will not match with your gravitationally inferred mass. Only if the two are different, right? So if you are able to change your law of gravitation, you might be able to change your prediction of the dark matter, of the total matter around which the stars are revolving. But I don't think that the visible matter itself is underestimated, because that is related to the light that is emitted, and that's astrophysics as I think in its purest form, as far as I can see, and astronomy, both.
Mm-hmm.
But what you can change is that model, the gravitation itself. And that's the theory MOND, that is, you modified theories of gravity. And where you remove this discrepancy between the visible mass and the gravitational mass by modifying slightly the gravitation laws. And you don't need very strong modifications. But as I said again, the bullet cluster collision was considered to be a very strong indication that MOND doesn't quite work. Now there is a modified MOND which explains the bullet cluster collisions, but there are still some other observations that it does not explain. But I think it takes me into areas where my knowledge is based only on review articles rather than doing anything myself. So I would refrain from going into more details about how these measurements are actually done. I mean, as I said, I know it only from review articles.
Okay, so the next question is by Bharendra Chotare. So his question is, first he starts with appreciation. Thanks for the nice talk. Is the distribution of dark matter in the universe isotropic and homogeneous? Okay, question mark. Then why do you think that the dark matter had to have been created in the early universe?
No, they're both very good questions, okay, to begin with. Now, the real information about the dark matter distribution, the profile of the dark matter, what I know, again comes from the simulations of the galaxy formations and the structure formations. So these are sort of, people assume a certain profile for the dark matter and then try to fit the observed try to fit the observed features of the galaxy simulations to that distribution. And there are certain sort of distributions that are quote unquote standard, but that is where the whole lot of uncertainty exists. And that is where the lot of work that astrophysicists do, people who actually try to see how galaxies are formed, how galaxy clusters are formed, how structure is formed in general. So the cosmologists and astrophysicists work very hard on that. And this is, according to me, an evolving area. And very often one tries to understand, and there are certain quote unquote accepted profiles of the dark matter, but how accepted they are and how correct they are, these are the practitioners in the game who will tell you what's happening. And actually, these do play a role. That's why I said the question is very good question. But there was one more part of that question. What was that? I forget.
Dark matter had to
Why the dark matter has to have been created in the early universe? It has to be created before the structures were formed. Because as I said, dark matter provides the potential well for the things to cluster together, the gravitational attraction of the dark matter. So the relic density, which which is co-moving with the expanding universe, it had to have existed at that point. So therefore, it had to be created in the early universe.
Okay, ma'am. So the next question is by Vijaya Kumar Sahu. So his question is, what would be the typical mass range of dark matter candidates?
Vijaya, that's why I showed you that plot. There is absolutely, if you ask, there is no firm predicted range. In supersymmetry, as I said, we have a range that we predict. But to be honest, if you want completely agnostic limit, then you would say that the dark matter should not be too light, so that the wavelength, the de Broglie wavelength of that dark matter particle is smaller than the size of the current size of the universe. Just by these kind of limitations, you can get a mass limit. And the smallest number that I had shown on that plot was actually from what is called a fluffy universe. So in principle, I don't think we know anything about the dark matter mass. It can be anywhere. But on the other hand, because of the relic density, as I explained, and the observed relic of 0.12, 1.112 plus minus 0.001, and the connection between the relic density and the formula that I presented, 1 over annihilating cross-section formula, in the derivation, if you have a weakly interacting particle of the mass between 10 to 100 GeV, you automatically get the right relic. So if you like, the only sort of indication for the mass of the dark matter particle in the early days and from sort of very generic arguments is this 10 to 1000 GeV. That's what I would say, depending on the fact that it is interacting weakly. And that interaction, whether it's interacting weakly or not, it actually decides at what temperature the guy will fall out of the thermal equilibrium. And then what the mass at that point is will decide whether it provides sufficient mass dark matter in the universe or not. Because what you compute is the relic number density. What will be the number density of that species at the time it falls out of equilibrium? Then depending on its mass, you will get the total mass contribution. And that is what I meant by that one slide, that what is liked very easily is a particle which has the cross section of the size of the weak cross section, and it has the mass between 10 to 1000 GeV. That decides then the temperature at which that the particle is non-relativistic at the temperature at which the falling out of equilibrium happens. So it's all sort of, there are 2-3 different threads, all of which combine together. And the most, what we would have loved, and that's why I think everybody loved that. And WIMP is something that people really loved for a long time. And that is why people like me still try to see today that before we say it does not exist, we have to rule out all nooks and crannies. It may be hiding in some nook and cranny. So for me, 10 to 1000 still is a nice range for a. So Vijay, I hope I have given you some answer to your question.
I hope it is okay with him. So okay, let's move to the next question. So the next question is by Rajnish Sharma. So he says, thank you, ma'am, for such an enlightening talk. I would like to know in what ways dark matter can contribute to future of universe.
I don't think there is anything in the future of the universe that it is going to contribute. If anybody knows anything to the contrary, I invite them to add to my knowledge, but not to my knowledge.
Okay.
So we are done.
Questions in the chat box.
We are done with that.
So people are just thanking. I mean, it seems that they are satisfied with your answers. They are just thanking you. all of them who asked the questions. So, okay, so now it is the time for questions from people who are in this WebEx studio.
Can I
So,
ask a question, Ravindra?
go ahead. Yes, Mahanti, please go ahead.
Hi, Rohini. So, when you're doing this SUSY analysis from LHC and direct detection, how tied are you to this freeze out formula for relic density? Supposing
No, actually, that's a very good question, because that is where I kind of ran through things, and I didn't, that was not the purpose, so I didn't really give you the details. But in fact, we did different types of assumptions. I mean, first is with the tying down directly to the freeze out formula. That is the standard cosmology. Okay, that's what we did first. But in the second stage, what we did, and I think there is much more to be done there, in fact, is that when we add this right-handed neutrino, for example, okay, then in fact, you need not have a freeze out dark matter, but you might have a freeze in, or you might have a more contribution from scattering, not just from the annihilation. So there is actually a whole lot of things that one can do. And in many cases, still many light dark matter candidate is still very much allowed with very viable signatures. But in the MSSM, I asked the one question first. Let me take everything standard cosmology, standard MSSM. And even then there are some regions that are still allowed, which can be then probed. But the second one was I add a extra hits in an MSSM, and just that changes the picture completely. And I again have in the standard picture possibility of valuable dark matter. Now the third would be what you asked, and this we did in MSSM by sort of taking again a very agnostic view that I don't know what the cosmology is. So I would basically forget the relic predictions. I would say that maybe there is some heavy moduli that decay and dilute, or increase the entropy and dilute the density. I would just say I don't care. I don't know cosmology. And then I asked the question whether those regions of the parameter space can be probed at the LHC and in the invisible decays. And lo and behold, we find that the entire region of the parameter space can still be probed. And that is, there is a whole lot that is still allowed by the current constraints. So in essence, the statement is that the electroweak particles of that mass scale are still very much allowed by all the different considerations. So thanks for asking this question, because actually that is one of the things when I added one sentence that standard cosmology can give signals at the non-standard cosmology can give signals at the LHC too. That was the essence of that comment. That I kind of take a very agnostic view that we theorists are crazy, we don't know anything. Let's just ask what the experiments can see. And I think that is also sometimes a good, especially when you have a tool like LHC, that is perhaps a very interesting approach to take also. But thanks for asking the question.
Can I ask one small question? Do you take this positron excess by AMS02 seriously in your analysis?
That I agree. And that in my parameter space, there will be no solution to that.
So that could be from pulsar. So you assume that
that
is
would be then astrophysical. In my way of looking at it, that would be astrophysical in origin, because my dark matter particle is very light. That's correct. And what I have checked, however, for example, in the NMSSM, is there, I mean, not that particular signal that you're talking about will never be explained in any of my parameter space. But other, the various indirect detections at small masses that people have been kind of talking of, they can be accommodated. That much I can say. If needed.
So any other question?
Navina, can I ask a question?
Sure, please. Partho, go ahead.
Rohini, thanks for a good presentation for a very kind of generalized viewpoint, at least from a particle physicist. Actually, at this point, since you talked about the very kind of global view of this dark matter and how we look as a particle physicist, so what do you think whether present state of this understanding of dark matter, is it a more experimental question or more theoretical question?
I think you have a very good, again, you have asked a very good question. I mean, obviously you are working on this, so you're going to ask that. See, there are, as far as I can see, this is an area where experiments are definitely leading us, leading the theories. I think that there is no question about. But in some sense, it is the most wonderful time to be a theorist and looking at dark matter. Because the beautiful part about dark matter that I like, and which I'm sure I don't need to tell you, is the connections in so very diverse areas. So if you say that I have one dark matter candidate, I better make sure that my early cosmological signals are correct, the early electron positron signals are right. At the same time, the relic is not, it doesn't overclose the universe. So I think it is challenging to the theorists, but it is really a great working ground for the theorists at present. So I would really say that it's a wonderful time to be doing dark physics. That's all I would say. I think but the fact that the experiments are so good is really helping us, both in the indirect detection and direct detection. I think both these experiments are really leading to LHC at this point. We just try to see if we can get confirmatory tests at the LHC. LHC is not leading the game, clearly.
Thank you, Rohini. I have another question, sir, just a brief question. So, so basically we talk about this 3 detection technique, what you have shown in this thing. Kind of we overemphasize that one, that has a limitation of some mass range and interaction range, which we are probing. Somehow we overemphasize that one. So is it some kind of...
Fair question. And in fact, I think that is what phenomenology is finally all about, right? I mean, you are asking precisely this question it's really an evolving field. And for a general audience such as this, I thought I could only make these very broad statements. But the reason, for example, I'm not paying too much attention to indirect detection is that for the kind of dark matter candidates that I am looking at, indirect detection doesn't really play a role. Because different experiments they are not, these are different windows looking into the same room, but doesn't mean that all the windows have access to the same part of the room. I think that is how I would like to put, where basically I'm agreeing with you, but I think that's what a progressing field of research really means. With standard model, we were spoilt for too long, where we were looking only under the lamp. This is the time where we have to look outside, away from the lamp also.
Thank you.
So
But that's what, like Weinberg says, go for the messes. This is the mess right now.
Yes.
So any other question?
Navinder, can I ask one question?
Sure.
So, Professor Rohini, you mentioned in passing that dark matter is also present in the sun. So, how can one ascertain its existence, and in what
Actually,
way?
there were people who were trying to look at what would be the signals due to the dark matter annihilation at the center of the sun. So you would produce an electron-positron pair, for example. So then you would see a particular, say, 500 keV line. So people have suggested such experiments. Needless to say, we don't have any signal. But yes. See, because you have to be really at the center for something like sun, any appreciable dark matter density will be only at the center, if at all.
At the core.
At the core. So there are actually, this goes into the indirect detection part that I didn't discuss.
Yes, yeah.
Okay.
Yeah, but the photon has to, I guess the photon has to do a diffusive motion from the center to the surface.
That's why many of these signals are not
change.
straightforward. The prediction of the signals is very, very poor.
Yes.
How to model what you will see, and therefore how to interpret what you see. You are completely right, Navinder.
Okay, any other question? So if there is no other question, I would like to request my colleague Durga Prasad for a vote of thanks.
Thank you, Dr. Navinder. So on behalf of the Director PRL Amrut Vyakhyaan Committee, and the entire PRL family, I thank Professor Rohini Godbole for accepting our invitation and delivering the 19th Vyakhyaan of this PRL Ka Amrut Vyakhyaan series. Thank you very much, Madam, for accepting our invitation and delivering such an exciting Vyakhyaan, looking at and describing the intricacies, implications, and current understanding of the dark matter, which is a mystery. Also, lot of thanks for patiently answering all the questions from our viewers, both from YouTube as well as WebEx panel. I thank our Director, Professor Anil Bhardwaj, for his constant encouragement and support for taking this series of Vyakhyans ahead. I thank our Dean, Professor Pallam Raju, Professor Nandita, Chair, and Dr. Lokesh, Co-Chair of PRL Amrut Vyakhyaan Committee, and all other committee members and others behind for their constant efforts. Most importantly, many thanks to our participants and viewers on WebEx as well as YouTube who have joined us for today for this Vyakhyaan. With this, we come to the end of this episode. It's now time to take leave from PRL. We will be back next week with another interesting Vyakhyaan. Till then, stay tuned and keep following us. Thank you very much. Bye.
Bye, Rohini.
Thank you and bye-bye, everybody.